So if you have a complex eigenvalue, alpha plus or minus I beta, we want to classify the fixed point at the origin when the alpha, the real part, is negative. What do you get? Spiral sink. When alpha is positive, spiral source.
And the last one's the center.
And the last one's the center.
Oscillating.
I had to make sure I knew what it was.
No, you also said it's spiral. No, Brendan.
No.
It's not oscillating around the center. It's spiral center. It's also the spiral side. No.
Oh! Lay your foot down, Kate.
Couldn't find
He still gets a 4. He still gets a 4. Lay that foot down.
Okay.
It doesn't dump, it just tries
Okay, so I have a linear system written here. Y prime is -2, -3, 3, -2 times y. Remember these bold y and y prime means that that's a vector. So this is actually xy equals -2, -3, 3, -2. Sorry, that's x prime, y prime, that's xy. And then you can translate that to two separate equations. X prime would be -2x minus 3y, and y prime would be 3x minus 2y. Alright. So if we have a computer create a direction field for us, it appears that there are no straight line solutions. So last class we learned how to find straight line solutions, and that was awesome because if you find 2, all you need is 2, and then you have the general solution. Just take a linear combination. So we have a little bit of a roadblock here in that there are no straight line solutions to find. Okay, so however, let's just do the same exact approach that we did. We'll see what happens, right? We have no other tools in our belt, so we'll start by finding eigenvalues, eigenvectors, and two particular solutions and see what they look like. They can't possibly be straight line solutions because it appears that there aren't any, but we can still do the same process and find two solutions. All right, so we start by finding eigenvalues, right? And you do that by taking the determinant of a minus lambda I, setting it equal to 0. So I'll take the determinant. A minus lambda I is -2 minus lambda, -3, 3, -2 minus lambda. And then the determinant is just AD minus BC. So we have -2 minus lambda times -2 minus lambda minus -9 equals 0. Going to multiply out my parentheses and combine like terms. You end up with lambda squared plus 4 lambda plus 13 equals 0. All right, so last class, that quadratic that we got would have been all nice and factorable, and we would have gotten 2 real eigenvalues. But that is not factorable, so what do you have to turn to? Quadratic formula. So lambda is going to be -b plus or minus the square root of b squared minus 4 times a times c all over 2a. Yep. So lambda ends up being -4 plus or minus radical -36 over 2, which simplifies to -4 plus or minus 6i over 2, right? When you take the square root of a negative, that brings an I in. Simplify that, you can divide the 2 into both terms there. So you end up with -2 plus or minus 3i. So we have 2 eigenvalues. So that makes sense. We had a quadratic. We expect 0, 1, or 2 solutions. So we've got 2 eigenvalues. So our process that we discovered last class said, okay, take each eigenvalue, use it to find an eigenvector, and then you build solutions of the form e to the lambda tv. Okay, so now I'm going to take each eigenvalue, find an associated eigenvector. I'm out of room. I'm going to go to a new slide. Sorry. Okay, so let's look at, the first lambda. which would be -2 plus 3i. And I want to find an eigenvector, so I'm setting up the equation AV equals lambda v. So up until today, my lambda has just been a nice, easy, real number. So this is going to look a little ugly, but it's the exact same process that we did before. Okay, so A is -2, -3, 3, -2. V is the eigenvector that I'm looking for. Lambda, in this case, is -2 plus 3i times my unknown eigenvector. So this is actually two equations, two unknowns. It turns out that the two equations are redundant. You don't need them both, but they will both give you the same solution. So this says -2x minus 3y equals -2x plus 3ix. Right, that's my lambda times the first component there. All right, so if I want to try to solve this thing for y in terms of x, or x in terms of y, it doesn't matter. I just need to get an equation that relates x and y. I have a -2x on both sides of my equation. Those can just drop out, right? Add 2x to both sides and it's gone. I can divide both sides by -3 here to get y by itself. And I end up with y equals -ix. Yeah, divided by -3, yeah. Okay, so I just need to pick a vector that satisfies that equation. What do you think?
Negative I for y and 1 for x.
-I for y and 1 for x. That would work because, yeah, if you make x a 1, 1 times -I is -I, so it gives you y. Another one that would work would be I1, right? Because any multiple of this will work. So if you multiply both components of that by I, you get 1 times I is I, -I times I is -I squared, which is +1. I kind of like this one just because there's no negatives in it.
Isn't I times -I is -1?
Yeah.
I times I is -1.
So I times negative I is 1.
All right, so we've got an eigenvector, one of them, right? Let's look for lambda 2, which is -2 minus 3i. We'll find the eigenvector that goes with that one too. So again, we're solving AV equals lambda v, -2, -3, 3, -2, times my unknown eigenvector equals -2 minus 3i times xy. All right, so I get one equation here. I get -2x minus 3y equals -2x minus 3ix. Same thing that happened before, the -2x's drop off of both sides. Just add 2x to both sides and they're gone. Divide both sides by -3. And you get y equals ix. So an eigenvector that would satisfy that would be 1i.
So why does it go y on the right side of the equation? And 1 times.
Because I was just doing the first component. So I dot product -2 and -3 with xy. That gives me the first component of my answer. So I just do the -2 minus 3i times the x.
Okay.
It's the 3x minus 2y would give me lambda times y. But I only wrote out the first equation because I only needed one. The two equations are redundant in this case. All right, so I have two lambdas, two eigenvalues, and two associated eigenvectors. So I can write down two solutions. They're ugly because they have i's in them, but they are technically solutions. Okay, so two solutions. Y1
We derived this Calc 2 Taylor series.
Yeah, you're right.
All right, so remember, your solutions are the form y equals e to the lambda tv. So my y1, I'll use my first lambda, which was e to the negative 2 plus 3I. That was my first lambda t. And my associated eigenvector is I1.
Is this part of the three?
Yeah, it's still part of 3.
Oh,
sorry.
Very efficient.
Don't worry, there's only 19 steps in the demo today.
My second solution, these used to be straight line solutions, right, when lambda was real numbers. They're not straight line solutions anymore, but they are solutions. Okay? They just are ugly. So my second solution is e to the negative 2 minus 3I. That's my other lambda. And the associated eigenvector was 1I.
Euler's formula to the rescue.
Okay, so now I have two solutions. All right, now we're done with number 3. We found eigenvalues, eigenvectors, and we used them to put together two solutions. Two complex solutions. All right, looking at number 4. Euler's formula. So we derived this in Calc 2 using Taylor series. You remember?
Yeah.
Yeah, okay, good. So e to the I theta is always equal to cosine theta plus I sine theta. Or cis theta, sometimes you can say that. All right, so now I'm going to combine Euler's formula with some simple laws of exponents. So if I want to raise e to a complex number, a plus ib, and why would I want to do that? I don't know, because it shows up in my two solutions, right? So raising e to a complex number, the law about exponents that says when you have like bases, you would add the exponents. I have added exponents here. So I'm going to rewrite it as e to the a times e to the bi. That makes sense?
Yeah.
Okay. So then I'm going to keep the e to the a, but replace e to the bi or e to the ib with Euler's formula. Just instead of a theta, I'm using a b now. So this is cosine b plus I sine b. It's not that bad. Distribute the e to the a, and we get e to the a cosine b plus I e to the a sine b.
Are we need to know this, or is this just so we know that this is legit?
You're going to need to be able to do this.
Oh.
Yep. All right, so this is an important thing that you need to be able to translate. That's supposed to be a star.
Thanks, Kevin. I'm on the test, is what you're telling us?
You need to be able to look at e to a complex number and rewrite it like this to finish the problem. Okay, so now we're just going to pick one of our complex solutions. We found two of them. We're going to just look at one of them for now. And we're going to rewrite it using this little truth that we just figured out. All right, so let's look at our y1. Our first solution was e to the negative 2 plus 3i t times the eigenvector I1. Okay. First thing I'm going to do is my e to the lambda t, distribute the t. So this becomes e to the negative 2t plus 3ti times I1. Nothing big so far, right? Okay. So next thing I'm going to do is I'm going to rewrite this using this truth up here.
I see what we're doing here.
So this is e to a real part plus an imaginary part. This is e to a complex number. So I'm going to rewrite it using that formula I had up there. Okay, so this is going to become e to the negative 2t cosine 3t plus I e to the negative 2t sine 3t times my eigenvector I1. Okay, so in this case A was negative 2t, right? And B was 3t.
So we're going to find out that periodically the values are going to change in between, 1 and negative 1, is what it looks like?
Yeah, this is sinusoidal, yeah.
Yeah. And what is Bravo, or not Bravo, but beta in this case? Because then we can find out the period, the period.
Yeah, we're not there yet. Okay, so next step is to distribute that thing I just did with Euler's formula, distribute to the I and the 1. Okay, so this becomes one big vector, I e to the negative 2t cosine 3t. And this is going to become plus I squared, but what's I squared? Negative 1. So I'm just going to do minus e to the negative 2t sine 3t. And then when I multiply that whole guy by the 1, nothing changes, so I get e to the negative 2t cosine 3t plus I e to the negative 2t sine 3t. All right, my next step. In the first component, I'm just going to reverse the order of the addition there. So that the real part comes first. So e to the negative 2t sine 3t, that has no i's in it. So I would like that to come first. So I'm just going to change the order of that addition there. So this becomes negative e to the negative 2t sine 3t plus I e to the negative 2t cosine 3t. So it has my traditional a plus bi look. Right, real plus imaginary. Second component was fine. All right, break it into the sum of the real part and the imaginary part. My real part is e to the negative e to the negative 2t sine 3t and e to the negative 2t cosine 3t. That's my real part. And then my imaginary part, I have an I in both terms. I'm going to factor out the I. And I'm left with e to the negative 2t cosine 3t, e to the negative 2t sine 3t. I know, I told you before we started, there's a lot of tedium involved in this process. It's messy.
I can't wait till this class gets you guys in circles.
We are looking at linear systems that have complex eigenvalues.
I have a question.
Yes.
Why did we factor out an I on the because there's only one part of the well, no, there's only one part of the equation that actually has I in it, isn't it?
Yeah. There's an I in both of these terms, right? I already broke off the part that didn't have an I. So it's okay.
Oh, because it's distributed.
Yeah. All right, so this is the real part. Real part of the solution, imaginary part. Can we stop the conversation, please? So we have a real part and an imaginary part of the solution. So, I mean, it kind of feels like, what's the point? Like, I just took something really messy, right? The solution where it looked like e to the lambda TV, and I just rewrote it, but it just looks messier now, right? So there wasn't really a goal that we were working towards. I was just saying, do this and do this and do this, and you were like, okay, yeah, I guess you can do that. I don't see why you are, but you can, right? So you can rewrite it like this so that it looks like a real part plus I and an imaginary part. All right, so the point of that is there's this amazing fact that says if a linear system has a complex solution so that you can write it as y real plus I y imaginary, which is what we just did, right? Then it actually has two other linearly independent real solutions. The real part and the imaginary part taken separately are two additional solutions to the system. So we already had two solutions. From each of those two solutions, we can generate two more. Right? So we've actually got like 6 solutions to this system now.
And 4 of them are going to be real.
But to write, and 4 of them are real, yeah.
I don't see any straight lines.
I didn't say they were straight line solutions.
Linear
So just give you real solution.
It's a linear system. I didn't say they were linear solutions.
Oh.
Okay, so we have 6 solutions. 4 of them are real. We only need 2. If you have 2 real, linearly independent solutions, you can write the general solution. Just take a linear combination of them and you're done. All right, so you can verify that they're linearly independent solutions on your own, or you can just take my word for it. So we have 2 particular linearly independent real solutions. What do we do with them? Take a linear combination and you've got the general solution. So my general solution, y of t, is going to be k1 times the real part, right, plus k2 times the imaginary part. And you just leave out the I. That's the amazing thing. Like, you just drop the I from the imaginary part, and that's also a solution. So this becomes k1 times the real solution. The real part of the solution was negative e to the negative 2t sine 3t, and e to the negative 2t cosine 3t, plus k2 times the imaginary part, where you don't even write the I down, and it was e to the negative 2t cosine 3t, e to the negative 2t sine 3t.
Okay, so let me ask you this.
Yeah.
Are we assuming then that the I is nothing more than an arbitrary constant to the system of linear equations?
No, I is always the I that it always has been. It's just we can ignore it because it turns out, and I'm not proving it to you right now, right? So if that's what you're asking me, I'm not going to answer, right? That when you have a solution that looks like this, a real part plus I times an imaginary part, that it turns out that this and this, without the I, are also solutions. And you can verify it.
The reason why I'm asking is because, when you go back and you look at this equation with the one that we just wrote down, the separation of the two equations, then obviously the I is taking place, or the K2 section is taking place in the I.
No, not really. Yeah. You're leaving out you're not just replacing the I with a K2. I mean, in effect, that's what it looks like you're doing. But what you're actually doing is you're saying, okay, this is actually a Y1, this is actually a Y2, and I'm going to take a linear combination of them. The I just is irrelevant. Okay. In practice, it looks like you're replacing I with a K2, but that's not what you're doing.
Will you ever tell us the derivation of it?
No, I want you to do it yourself.
Oh, we're going to do it ourselves. Okay.
Well, that's number 8. Verify that it's a solution. You would just take each of these vectors and check that it satisfies your differential equation.
Now, if you multiply the first, the real solution, by I, is that a solution?
I don't know. I don't think so. I don't think so.
But each one on their own, I times the imaginary, that's a solution by itself.
Without the I, just the imaginary part without the I is a solution by itself. The real part is a solution by itself, and the imaginary part without the I.
But if you incorporate the I and the imaginary, it's no longer a solution.
Well, when you add them together, it is a solution. Yeah. The real plus I
So
imaginary.
it's all together, get rid of the I.
Or get rid of the I and take them separately. Yeah. All right, so notice that this little trick that we're using here, or I guess I shouldn't call it little, I mean that was kind of a massive amount of work, right? Where you use the real and the imaginary part of a complex solution, it means you only have to find one eigenvalue and one eigenvector. Because we only needed y1, right? We started with this guy, y1, and then we ended up deriving two solutions from it. So you didn't need the y2 that we got at the beginning. So on the previous slide, I had a y1 and a y2. You don't need this anymore. Yeah. So that saves you, a teeny little bit of work.
How often is this the case where we have our second eigenvalue is irrelevant?
Whenever it's complex.
You mean that for sure?
Yeah. Yep, whenever it's complex, you don't need the second eigenvalue. Okay, so we were kind of sad that we didn't have straight line solutions, but it turns out we can still find the general solution to a linear system that has complex eigenvalues, even though there's no straight line solutions. It just takes a lot of messy manipulation. So in our example, the vector field appears to spiral around and towards the origin.
Sink.
Yep, so it's a spiral sink.
Thank you, sorry.
So this was the general solution that we just found. We just came up with this. I factored out e to the negative 2t, but it's the same thing as what we just wrote down. Okay. So this is the x of t and y of t graphs. This is time. This is x and y, right? So both solution functions, x of t and y of t, are sinusoidal because of this part, right? The k1 sine 3t, k2 cosine 3t. What's the period of those two functions?
Whatever beta is.
Yeah, what is beta?
3.
3. It's 3. Yeah. When you find the period of a sinusoidal function, right, remember just it was like sine or cosine of b, t minus c plus d. The period was 2 pi divided by b, right? The coefficient on the t. What's the coefficient on the t in every trig thing here? 3. So my period is 2 pi divided by 3. And what's the amplitude of each of these things?
4.
No.
The A is the amplitude, right? Yeah. So in this case, what's the amplitude?
K1, K2.
What about the e to the negative 2t? What does that do?
Okay,
Yeah, it's e to the, it's an exponential decay function. Right, and that's why when you look at the graphs, the amplitude is flattening out, it's going to 0. Because the amplitude is being replaced with an exponential decay function.
So it's a point of convergence. Is what it
Yeah,
is.
yeah, so it's converging down to 0.
That's because it is a sink, the source of
And that's because it's a sink. Yeah, you can see it in the phase portrait that these things are sort of converging down to 0. X of t and y of t are both approaching 0.
So the source would be an exponential growth function.
Yeah, yeah. And then what was it about our original problem, right? So here's our solution again. So the sinusoidal aspect causes the oscillation about the origin, right? So this piece causes oscillations. This piece causes the amplitude to decay, right? And then think back to all the work we did. We just did so much algebra to come up with that solution. What exactly was it that caused the amplitude to be e to the negative 2t?
That's a factor of integration, isn't it? On the Earth.
Well, there's a negative 2 in our lambda
It was the negative 2 in the lambda value.
Oh,
Yeah. It was, so if that had been a positive 2, this would have come out to e to the 2t, and we would have had a spiral source. Yeah.
So, right, if we have.
So we had lambda was negative 2 minus 3i, right? That negative 2 led directly to the e to the negative 2t in our solution.
And does the 3 correlate to?
And the 3 correlates to the period.
Oh, so you use
Yeah.
So you
right.
finally came together in this
Yep. So we have this. So we have a handy dandy summary here. If you have a complex eigenvalue, alpha plus or minus I beta, the solution curves always spiral around the origin in the phase plane. The period's always going to be 2 pi over beta, which is the imaginary part of your eigenvalue. Alpha negative, then this is a spiral sink, meaning you'll have exponential decay in the amplitude. When alpha is positive, the solutions spiral away from the origin, and we call that a spiral source, so you'd have exponential growth of your sinusoidal amplitude. And when A equals 0, the solutions are periodic, and the amplitude is constant, right? We call this a center.
Wasn't it, still again?
Yep.
Wasn't -2 plus 3x?
Was it? Yeah, you're right.
Otherwise it would be, cosine -3, right?
Yeah, you're right. Yeah. All right, so the direction of the spiral, to know which way it spirals, clockwise or counterclockwise, right? It's the easiest way to find it is to just compute one single vector in the direction field. Like just pick one point, plug it into your x prime and y prime, just like you did on a quiz and a test. See which way the arrow is pointing, and if it's going, that way, then you go, okay, I'm spiraling that way. The period's always 2 pi over b, or beta. And the natural frequency, I included this because your homework asked you a couple questions about the natural frequency. The definition of natural frequency is just the reciprocal of the period. So just flip it if they ask you for natural frequency. All right, so that's it for the demo. Try one on your own.
Jeez.